So let's talk about measurement amplifiers. How to think about those amplifiers? What is the purpose of all that stuff? Simply said, we want to amplify a signal which is too weak to be detected easily, to be used easily, further for analysis or whatsoever. So the idea is quite simple. When thinking about that stuff in senses of electrical engineering, meaning in senses of electrical signal, and remembering the stuff before, electrical signals are basically the stuff, those signals we have to deal in measurement technology. So let's see. Ideas, we have some measurement signal over here, UE, which is quite small, presumably. And so we want to plug that voltage into some black box. That's our measurement amplifier right now, which does nothing more than to produce some output voltage, UA, which amplifies that input voltage by a certain amount, by a certain factor. How does that thing do that? The idea is quite simple. So the signal coming in is weak. We need some external energy to amplify it. There's no possibility that that incoming weak signal will get larger, will get less weak without applying some external energy. So, talking about voltages, we have some extra voltage source connected to that output voltage, whereas that input voltage directly influences that voltage generation on the output. So what do we have? We have some kind of a voltage generator. So the voltage coming in generates, modifies the voltage going out. What do we want to have for this measurement amplifier? So a few things which are desirable are obvious. So we want some high amplification. So when there's a factor involved, we'll call it K line, with that line over here, which should be as high as possible, obviously. Moreover, we want to have some behavior within the amplification which tells us that the output voltage really exactly follows the input voltage in any dynamics, in any flexibility. So we want to have a dynamic behavior, meaning UA follows UE exactly. That's important also. Having said so, there are some not so obvious things we want to have for such a measurement amplifier, which are that you should not need a lot of power to drive your measurement amplifier, meaning that input voltage should be connected to something with a very high resistance over here in the input. There should be a very high input resistance so that nearly no current flows into that generator, and that voltage source over here has not to deliver any energy to the amplification over here. So the measurement object should not be influenced by the measurement amplifier itself. That's a very important thing. The measurement object, the measurement voltage we want to know about should not be influenced by the measurement amplifier itself. On the other hand, we know that we want to connect some measurement device on the output of the measurement amplifier. So we want to have an output voltage which really does not influence or it does not make any problems when measuring it using a voltage meter, for example. So that, speaking about electrical values, that output resistance should be very small, so that we can connect any voltage meter to the output and measure exactly the output voltage and nothing else, with no additional systematic errors which could be derived or which could result because of the internal voltage of the output side of our measurement amplifier. Yeah, that's the wish. That's the thing we want to have, such a measurement amplifier. And for sure, you all know it, there are some amplifiers out there which deliver us with something like that. Namely, operational amplifiers, which are marked in electrical engineering by such a triangle, and those amplifiers have two inputs, a plus and a minus side. They need an external voltage, which most of the time is not denoted, not marked within an electrical circuit, and they give us some output voltage, whereas the whole stuff is relative to the ground. So we have the output voltage over here, and we have two different voltages over here, namely UG and over here UE. And that's grounded over here. So that's the electrical circuit. Those measurement amplifiers over here, they imply a usable behavior. Those operational amplifiers at that place do not necessarily have a real usable behavior. What does that mean? Those measurement amplifiers marked over here, for example, assume or propose or imply a real usable amplification factor K over here. We want to have that line at the amplification factor only for the operational amplifiers, not for the measurement amplifiers, which I will talk about furthermore in the next chapters. Having said so, for the typical operational amplifier, those amplification factors tend to be very large, and for the ideal operational amplifier, it is assumed to be infinity. It is assumed to be infinite. You know, that means any voltage coming in here for the ideal operational amplifier is amplified by a factor of infinity. That makes no sense when thinking about it, but it makes more sense when using that operational amplifier within a certain electrical circuit, reconnecting the output to the input. We'll talk about that in the next part of the chapter of measurement amplifiers. So that's one thing. For a real operational amplifier, those will tend to go to factors like 10 to the 5, 10 to the 6, 10 to the 7. So they are really very large. Now thinking about that, still it looks like not usable. Why should I have an amplification factor of 10 to the 6? That's too much. Having 1 volt, I would have an output voltage of 1 million volt. That's not usable at all. But as I said, normally you don't use that large, that big amplification factor. But why is it that those amplification factors are so large, chosen to be so large? It's easy said. By recoupling the output to the input, we can adjust the amplification by the amount of recoupling to the input of the operational amplifier. So, as long as we can reduce that amplification factor by rewiring, by recoupling, it is sensible somehow to give those operational amplifiers very large amplifications, meaning as large of an amplification as possible at all. That's one thing. Then the other thing, which is assumed for an ideal operational amplifier, is that we have some input resistance, which is infinite. We have some output resistance, which is 0. For real operational amplifiers, those tend to be a couple of ohms at the output and a couple of mega ohms to giga ohms, or even more at the output. So, all right, that's fine, because thinking of what we want to do, we have a small signal over here, so we have a very high input resistance. You can think of that as of a measurement device with a very high input resistance, so that's nice. That reduces our systematic errors. And on the other side, we have a very low output resistance, so we can use any measurement device over here to get that output voltage over here, to get that output of our operational amplifier over here. Then there are some more behavioral facts about operational amplifiers concerning, for example, the dynamics. Talking about an input voltage over here, which is the same. So that voltage between plus and minus, that voltage difference is amplified along here. I think that's obvious because of the plus and the minus over here. So now let's assume there's no difference between the UG and the UE over here. So there should be 0 at the output. For sure, for real operational amplifiers, sometimes it's not 0 exactly. So we have some offset for real operational amplifiers. For our ideal operational amplifiers, that's 0. So when there's a 0 difference, we get a 0 amplification for the ideal operational amplifier, not for the real, in reality used operational amplifiers. Then moreover, we could apply some alternating current over here, synchronized at the plus and the minus input, so that the difference between those two voltages at plus and minus again is 0. Again, we would expect to get a 0 output voltage, but again, we don't get a 0 output voltage. Moreover, that output voltage also depends on the frequency, on the form of the alternating currents which are coming in here at the plus and the minus plugs we have over here. So that's some different behavior for the real operational amplifiers. Again, for the ideal operational amplifier, as long as there is 0 at the input difference, 0 comes out. And now for all further assumptions, for all further discussions about operational amplifiers, we will assume to deal only with ideal operational amplifiers, meaning we have nearly infinity amplification, we have nearly infinity input resistance, we have no output resistance, and the behavior is dynamically and concerning the offset perfect, meaning when there's no difference at the input, no amplification current will be given at the output. So the next step now is to use those operational amplifiers and build up some circuits to make those infinite amplifications to some usable, not infinite amplifications. That will be part of the next chapter. See you then.